Sir, we are live now. Please start.
Okay. Yeah. Thank you. Hello, everyone. Good evening. Welcome to the live session of computational fluid dynamics using finite volume methods course. Okay. So today I'm going to basically first go through all the questions that we have collected, and then after that I'm going to look at the chat messages here. Okay. All right. So okay. So coming to the questions. I'll just share my screen. Hello. All right. So the first question is, what quantities does various turbulence models solve for, and how are turbulence effects considered in Navier-Stokes equations? Okay. So this is basically not very much a question related to CFD, but I would write it here. So the first question is, so if you have turbulence models, you can kind of categorize them basically as statistical models or eddy resolving models. So in the statistical models, you have RANS-based models, and in the eddy resolving, you have LES-based or models. Okay, so if you look at RANS-based equations, then it is going to solve for your K epsilon, which is basically the turbulent kinetic energy or the dissipation rate, and so on. Okay, so depending on the model. In the case of LES, we may or may not actually solve for an equation. Okay, so in that context, it will not solve for an equation. Okay, so how are the turbulence effects considered in the Navier-Stokes equation? So if you perform a statistical averaging, that is basically in RANS, you end up with something known as the Reynolds stress tensor, that is rho times ui prime uj prime over bar. Okay, and this is what will be modeled using something known as eddy viscosity times the velocity gradients. Okay, so that is dou ui bar by dou xj, dou uj bar by dou xa. We haven't actually looked at this index notation as such, but if you're interested, you can kind of look at it. Okay, so the turbulence effects will come through the Reynolds stress tensor in the context of turbulence models. Okay. All right. So let us look at the second question. The second question is. Is there any open source CFD solver using Python available? Well, I'm not quite sure if there is a open source software using Python, but what I came across after a quick Google search is something known as a Fluid Sim. Okay, you can probably look at it. It seems to be written in Python, but I don't think it is basically a finite volume solver. Okay, or nor a finite difference. So it is basically a some pseudo spectral element code. So maybe you can kind of look at it further. So the third question is, consider I am doing research in quadcopter. Do I have to verify the results experimentally or numerically, or numerical computation, sorry, for research to get accepted? Well, if you do research in quadcopter or something like that, okay, essentially, if you have a good numerical or benchmark numerical simulations, then you can use those results to verify your results. Otherwise, you have to look at some kind of experiments using which you can kind of validate or verify your results. Okay. All right. The fourth question is, we are classifying the flow problems based on governing equations alone. So based on the classification, we concluded that the flow field is whether continuous or discontinuous, and proceed with aim of our solver going to capture all these discontinuities. If there is any, okay, yes, is it right? Yes, it is. Then why don't we consider boundary conditions or domain geometry? Definitely, it is complex, but is it possible to classify partial differential equations based on boundary conditions or end geometries? Okay, or at least can we classify based on boundary conditions? Yes, of course. So when you say you're classifying based on the type of the when you're solving or classifying based on the type of the equation, right? This already includes the boundary conditions, right? The moment you fix the type, the boundary conditions in terms of what are required is already fixed. Okay, of course, the values really doesn't matter, but we are looking at essentially what type of boundary conditions are required. For example, if you are looking at an elliptic problem, right? which is basically looks like, let's say, del square phi equals some source term here. Then for this, if you have, let's say, some boundary, then the boundary conditions is required on the entire boundary for either for phi or for the first gradient of phi. Okay, so you need to specify this boundary condition. Now, if you're looking at a parabolic problem, then a parabolic equation, then, for example, let's say I have a domain like this, where I have an inlet coming from here, and there is an outlet, and you have some walls here. Then essentially you need to provide boundary conditions on this top and bottom, and also on the inlet. You don't have to provide essentially a boundary condition here because it's kind of a parabolic in nature, so the flow is going to kind of bring whatever you have inside as going to be outside. Okay, so depending on the type of the equation, the nature of the boundary conditions is already built in to the problem. Okay, so in the classification. All right, let's look at the next question. In practice, conductivity is non-linear function of temperature. So can we follow the same technique to linearize conductivity? Okay, well, yes. So the non-linearity that we talked about is for source term. Okay, so if source is a non-linear function of temperature, then we have learned how to linearize and use it. Okay, whereas if you have, let's say, your thermal conductivity is a function of temperature, or your viscosity is a function of temperature, and so on, then you would not linearize it. You will not linearize. Rather, what you would do is you would use the current iterate value of temperature, right? That is basically your T star, and calculate your thermal conductivity using that T star. And because you are now, your T star itself is not exact, the thermal conductivity you have used is also not correct. As a result, what you have to do is you have your main loop, right, for your TDMA or any other solver that you use. You have to kind of bring in a second loop on top of this thing, which is called an outer loop. And in the outer loop, you would calculate your properties such as K, mu, etc., which are functions of nonlinear functions of temperature, and you keep these fixed throughout this inner loop. Okay, and then when you go back, you are going to recalculate them based on the temperature that you obtained here. Okay, so that's how you're going to do it. You will not linearize it. Rather, you're going to basically do it from by introducing an outer loop. Okay, so let's look at the sixth question. The sixth question is, sir, I downloaded a book called Numerical Linear Algebra by Wendland from Cambridge, text in applied mathematics, and I got surprised that it is very vast field. Can you remark about should we expertise in numerical linear algebra for being a successful CFD engineer? Well, of course, numerical linear algebra is a very vast subject. You will not, you don't have to master the entire linear algebra. Rather, I would suggest if you can learn the workings of some numerical methods or numerical linear algebra, such as at least the basic ones, such as Jacobi, which we are learning in the course, or Gauss-Seidel, or the conjugate gradient method, okay, or the steepest descent method, or multigrid. So these are kind of will be sufficient to know that these methods are used popularly in the CFD codes, and they should be sufficient to basically kind of bring in a successful person in CFD engineer as such. Okay, so but of course there is no limit. So it kind of, I would say, suggest that you start off with some basic numerical linear algebra as such. Okay. All right. So the next question is, I'm currently using OpenFOAM for my bachelor's project, and during this course, I tried coding up the algorithms using Python, NumPy, and Matplotlib. What languages would you recommend someone who wants to pursue an academic career in CFD? Any tips, advice you wish you had gotten before getting into grad school? Also, what do you think of new scientific programming languages such as Julia? Well, I would say in terms of languages, instead of learning Python, because Python is basically a, of course, I think it can also work as a compiled language, but I would kind of feel Python more of a Python language more of a interpreted language. Therefore, I would suggest you to kind of most of the CFD codes are usually written either in compiled language such as C, C++, or Fortran. Okay, if you look at any of the open source or the commercial softwares, so I would suggest learning any of these compiled languages. Okay, rather than Python. Of course, Python will also complement what you're learning using the compiled languages, because using Python you can maybe quickly automate your pre and post processing steps. Okay, so as a result, I would suggest you to look at any of these compiled languages. Okay, all right. Then what is the next question? Next question is okay. So the next question is any tips or advice you wish you had gotten before getting into grad school? Well, I can't remember any. Maybe learning some of these languages much more in deep or something like that would probably will help you. I can't remember something on my top of head. Okay, so what do you think of a new scientific programming language such as Julia? Okay, it might be very useful to learn Julia, but I don't think there are any CFD codes are written in Julia. But certainly these might help you in terms of automating some of the CFD calculations. Okay, or maybe in terms of parallelization and things like that. So maybe it's always good to learn some of these languages. Okay, thank you. Then the 8th question is, I would like to do CFD modeling of the combustion operations of the burners of the cracker system in my plant. Whether softwares are available for this, or do I have to generate my own solver? I'm not quite sure whether there are any solvers. I'm not a combustion person as such. But of course, you can certainly look at any of the packages such as Upwind or Star CCM to get into to see if their capabilities of combustion are kind of sufficient for you. That's what I would suggest. Okay. Kindly give insight into CFD involving chemical reactions and chemical components. Where could I find books on or courses regarding this? Well, so chemical reactions or combustion is one field which we are not covering as such, but of course the chemical reactions is one. So learning about combustion or chemical reactions or chemical kinetics is one field, and then learning the numerical combustion, or how do you numerically solve this, is another field. Okay, so these are two separate things. I have kind of collected few books which I can kind of write down for you. So you can probably look at Introduction to Combustion by Stephen Turns. That's basically more about combustion itself. And then you can also, if you want numerical book, you can look at numerical simulation of reacting flow by Oren and Boris. These books probably will help you. You can also look at a book by Turbulent Combustion by Norbert Peters. Okay, so maybe these books might help you with your quest for learning combustion or CFD of chemical reactions. Please give some directions to study CFD further after my course. Okay, so if you want to study, if you want to kind of extend this, you could probably pick up the book by the Finite Volume Method in Computational Fluid Dynamics by this is one of the textbooks for your course. I have kind of listed it there by Mokal, Mangani, and Darwish. Okay, so you can probably pick up this book and kind of learn further. All right, then the next question is, what is the relevance of coding and solving problems in CFD? If excellent open and paid softwares are available, machine and coding, even TDMA method for large domains are very tiresome and time consuming. Well, the relevance of learning CFD is basically first thing is to, or learning coding or writing these programs is the learning part, right? You will know how to or what these equations are solved behind any of the software. That is the learning part that is involved. And once you know the equations, you would know their limitations or where they are applicable. And then depending on that, if you want to kind of change the problem and solve something else, you will be able to modify the equations. Okay, so that is the first part. The other thing is your comment on if excellent open and paid softwares are available. Well, they are available, but the limitations will only come to know once you start using them. For example, you have a particular problem you would like to solve. Once you start using them, you may either run into some issue or something, or you will realize that what you want to solve is exactly not there. Then all these things might come. So as a result, it is always good to learn and probably work with some software for which you have maybe a code or an in-house code, such that you can always implement these things into the code. Okay, so that's what I could say. All right, then the ninth question is, we have now been deriving methods for incompressible fluid flows. How would the methodology differ if we are talking about compressible flows, preferably combustion incompressible flows? Okay, so this is the ninth question. So as we are looking at incompressible flows, as you have seen, we are running into pressure velocity, checkerboarding issues, and so on, while we solve incompressible flows, right? Whereas if you look at compressible flow, you basically have continuity equation for density. Density kind of is an equation for, from the continuity equation. So you have density, three components of velocity and pressure and temperature, right, or energy. So you basically have 3 plus 3, 6, and then you have the continuity equation plus 3 components of the momentum equation plus 1 energy equation. That's basically 5, plus you have the equation of state. So all these are, in principle, you can solve compressible flows in a straightforward way because you have the same number of equations and you have an equation for each of these. Okay, but you run into other difficulties such as the stiffness of the system or the speed and capturing the shocks and resolving the shocks and so on. So the methods that are used for discretizing these two, or the way that is discretized, are all quite different. Okay, which we are not learning as part of this course. We are only learning the incompressible part of the solving the system of fluid flow equations. Okay. Then the next question is, it would be better if you provide every answer of the assignment, please. Okay, sure. I've asked the teaching assistants to take a look at and provide all the solutions for all the assignments, so that you'll be able to understand them, what is the method by which we got the answer, and then you can learn from there for your final exam. Then the next question is simple method used for solving potential flow, that is continuity and Euler equations? No, simple method is not for, so this is question number 11. So simple is basically not a method for potential flow. Simple is a method for solving incompressible fluid flow. Okay, incompressible flows. All right. So it is not for potential flow. Only thing is that it basically allows you a way by which you can write an equation. You can come up with an equation for pressure, right, which was absent otherwise, right? So that's what it will help you. Okay, so that's about the 11th question. Okay, then there are multiple questions here. I decided to make a CFD as my career. What should be the next immediate step after this course? Well, I would suggest if you would like to pursue this, maybe you can do a project in your master's or graduate studies, such that you can learn more and spend more time on a CFD, such that it will take you in the right direction. How to approach a company as a CFD fresher? Well, I would think if you have done some courses, let's say the NPTEL course or any other course in your college, then these should help you to get into a company. During the interview, you should be able to answer some of these questions. Is there a possibility that company may hire a graduated freshers who have theoretical knowledge of CFD? Yes, it is very much possible. Companies will actually look for some theoretical knowledge of CFD, because you can always learn the software part of it while you are on the job. So the theoretical knowledge is what kind of makes you different, or kind of puts you sets aside, such that you're selling your USP as such, your unique selling point as such. What does company want us from freshers in CFD field? Well, I don't know exactly, but I feel if you have, I mean, most of the companies look for students who are, who are graduates who have enthusiasm to work on a particular problem and then try to solve it. I think that's what they look for, and then some knowledge, whether you are thinking in a logical way and taking steps in achieving your goal. That's what I think they look at. But certainly, I don't think they will look at your background in terms of how many simulation softwares you have learned and things like that. Yes, companies, most of them, they will have some training period in which they'll teach the simulation softwares. Yeah, so why to do courses outside graduation? Well, the thing is, you don't have to do a course after graduation as such, but if you've already done it in your studies, then you don't have to do more courses. Only thing is that if you can learn the equations and then try to write the codes and stuff like that, then that will kind of sets you apart compared to others. And then also you would know the inner workings of the simulation software that you will be using in the company. Okay. For example, let's say if you want to tailor make some of the user-defined functions, some of the equations, then you will be able to write them because you know how to discretize, let's say, the unsteady term or the diffusion term and the convection term and so on. Okay. Now, the next question is, what kind of work is allocated in NPTEL internship? A simulation work, I am not sure. You have to check with the NPTEL office, the contact person. Okay, the person concerned. I'm not sure what is an NPTEL internship. All right. Now, how much time is required to be a good CFD engineer who can solve industrial problems? Well, that's kind of a very specific or kind of very relative question because it depends on how many projects you do, how much time you spend on either using a solver or using a software or something like that. So maybe I would think probably 1 or 2 years you'll probably be able to set up a case of industrial scale and kind of run it and post-process it and so on. Okay, but also there are several challenges in terms of generating the mesh, running the case, and post-processing and so on. So it all depends on number of projects you do and things like that. Okay. Can you please explain one more time why simple method is called semi-implicit? All right. So this is question number 12. Okay. Simple is called semi-implicit because we are dropping the contribution of the neighbors, right? So basically, when you write the equation for the velocity corrections, right, we have written it like sigma. We have written it as A east U east prime, right, equals sigma A and B U and B prime plus some contribution coming from PP prime minus P east prime, right, times some AE, right. In this, what we said is the velocity correction for the corresponding east phase is not coming from the neighbors, right. We said this is equal to 0, right. This is the approximation we have used in simple because that means what we're saying is that the pressure corrections the pressure corrections are solely responsible, right? The entire correction of velocity is done by the pressure, right? That's what we're saying. If we have not done that means if we have not done this thing, then UE prime would depend on the neighboring U and B primes, and the neighboring U and B prime here would also depend on the neighbors of its neighbors, and so on. As a result, you will end up with a full implicit system, right? And then you have to write another AX equal to B to solve this. That means it will become fully implicit. As a result, what we have said is that we have neglected the contribution of the neighbors, and then we put the burden of correcting the phase phase velocity corrections as completely coming from the cell pressure corrections. As a result, it is now not implicit anymore. It's kind of completely explicit, but then we just call it as semi-implicit because it's only in a halfway it is implicit because of this thing, right? It's not fully implicit as such. So that is why we call it as simple method. Now, in the Upwind difference scheme, why do we substitute the absolute value for Fe in the discrete equation? Let's take terms for each phase where diffusion flux minus convection flux. We write the convection flux as negative Fe times phi little e. If Fe is negative, then a whole term ends up to be positive, and so we have to add the mass flux term. Yeah, so okay. The thing is, the question is about the convention used while solving for the convection. So what we have done is we have this term, right, on the control volume. We have del dot rho u bar phi dV equals 0. We have written this as basically as sigma f rho u bar phi f dot AF equals 0 using the Gauss divergence theorem. And then we have, if you expand it off for all the phases, we have F east phi east minus F west phi west plus F north phi north minus F south phi south equals 0. The question is, we have taken F east equals F west equals rho u delta y, right? That means we have not considered the area with the direction. We only considered the magnitude of the area, because otherwise this would have been plus or minus, right? Which we have absorbed here rather than writing it here, okay? Because if you have considered here, it would have been all plus everywhere, right? Now, basically, we have defined a kind of a magnitude of a mass flow rate that is to do with the direction of the velocity. We would like to have the velocity direction solely define the magnitude of the mass flow rate. Okay, that is basically a convention. You need not do this thing. If you want, you can also define it as two separate things. Rho u delta y for the east phase and rho u delta y with a minus for the west phase. That can be done as well. So some convention we have adopted so that it will be straightforward. All right, moving on to the 13th question. In the context of stability analysis of explicit scheme, you told that if AP0 is less than the summation of the neighboring coefficients, then heuristically we say the solution will oscillate from for an increase in P0 value. Yes. How can we conclude that this is oscillatory nature without knowing whether P is 0 in the previous iteration? Is higher than the current value or not? Okay. How can we just tell by looking at two consecutive iterations only? Oscillation means values will go upside down without converging to a particular. Okay. That means the question is related to the values of the essentially what we have is we have the AP0. If it is AP0 or AP equals, right, we have written it as sigma A and B, phi and B 0 plus we have some B term plus we have AP0 minus A and B, sigma and B times PP0, right? That's what we have. So we said that if this is basically for an explicit scheme, okay? Now what we said is if all the coefficients are positive, then this is basically bounded. Phi b is bounded by the neighbors p and b 0. But if you have this to be less than 0, that means AP0 minus sigma A and B is less than 0, right? That means if AP is less than sigma A and B, then this is not good because you end up with a negative coefficient here, right? That means if we end up with a negative coefficient, then what we have is instead of getting bounded by these four neighbors, this value here, which is the phi p0 value, it may not be bounded by the time neighbor, right? Phi p0 is the time neighbor. As a result, it can, a negative value of the coefficient here. If this is kind of becomes larger, let's say if this goes to be a positive value, then this entire thing will be negative. As a result, this will decrease, right? And if this is a negative value, then the coefficient is negative, then this will increase. So such a behavior of increasing, if this value increases and all other values increase, then this also should increase in the next iteration. Now, such a behavior should only happen for parabolic equations. If it doesn't happen, you can actually go outside the bounds of your time neighbor and the space neighbors, and that is not correct. Okay, that's why we said in terms of increase or decrease. Okay, so using just two of the values. So you can think of it as a positive or negative value for phi p. That will kind of quickly give you how to address this. All right. Then the next question is, the solution will be oscillatory in nature if we have non-orthogonality. Is that cell having poor orthogonality only will have oscillatory nature, or it will affect the whole domain? It will affect the entire domain. Okay, so it's not. So initially, the poor orthogonality will affect one cell, and eventually the unbounded values will start spreading to the other cells as well. Okay. I think it will be difficult to say what percentage of 1,000 cells have poor orthogonality, because once you have incorrect solution somewhere, you end up with the entire solution kind of blows up. So you would basically get not a number or something like that everywhere, right? Okay. Then the next question is, let's say we are using Upwind difference scheme for convection term and linear profile assumption for diffusion term for phi phases. How can we assume two values for one particular phase centroid? Well, we are not using two different approximations for one phase centroid. Okay, what we are trying to do is we have two different terms. One is a diffusion term, right? And the other one is a convection term. and we are trying to discretize these two. That's all. Okay, we are assuming a linear profile assumption to discretize your dou phi by dou x east or west, and for convection we wrote it as, let's say, phi east, f east, phi east, and then we said phi east we would like to take it as phi p or phi west, right, or phi east. So essentially we are only trying to discretize these terms such that we can get an equation for, when you kind of assemble all these things, you'll get basically an algebraic equation such as a phi equals b or something like that. Okay. Then the next question is, could you please differentiate the terms that are unstable solution and oscillatory solution? Because we say that whether the solution is stable or unstable by von Neumann stability analysis, and whether oscillatory or not from heuristic way. Okay, so an oscillatory solution might also exist in let's say you can basically get an oscillatory solution. It's not an issue. So you have two different things. One is von Neumann stability analysis. The other one is the heuristic analysis. The heuristic analysis only tells you whether you get an oscillatory solution or a non-oscillatory solution by looking at negative coefficients if you get anything. Okay. Now the von Neumann stability analysis is more formal in terms of introducing something or the stability of the analysis. Now the only thing is, if von Neumann stability analysis says that it is unconditionally stable, you can still get an oscillatory solution, but the solution you'll get will be bounded. It will not blow up to nans or something like that. Okay. Now, stability, of course, does not mean that it is correct. Okay. Stability doesn't mean that it is correct or it is accurate. It will only be a stable solution. So that is kind of what we need to keep in mind. Okay. Stability does not guarantee accuracy. Okay. So for accuracy, you need to look at smaller and smaller meshes and see. Okay. Okay. Excuse me. So even though Scarborough criteria is a sufficient condition and not a necessary one, we do not proceed if our final discrete equation does not satisfy Scarborough. Yes, we will not proceed if we do not satisfy Scarborough, because your linear solver will not converge, right? You don't get a solution. Yes, that's correct. We use continuity, momentum, and energy equations for our research work, and you taught us how to derive those. But why do we use those equations? What are the importance of or significance of those equations? If you don't use those equations, what are the problems we're going to face? Well, the continuity, momentum, and energy equations are the governing laws, right? So these are the continuity, momentum, and the conservation of energy. These are the governing equations, right? These are all the governing laws for fluid flow, right? Now, if you say you don't want to use them, well, these are basically came up from the observations, right? These are all proposed from the empirical relation, from the observations of the experimental observations, and they are not they are the equations which will model or correctly model the flow of the fluid. So that is the significance. If you don't use those equations, I don't think it will be correct, isn't it? You will be using some other equation which is not correct behavior, correct description of the fluid flow. I think this question is not very clear to me in terms of why we should not use it. Okay. Now, the final question that we have here, before I come to questions in the chat box, is this is about linearizing the source term. You started with cubic equation like s equals 5 minus 10t cube. How do we get this term? That's basically just an example. So I have chosen some t cube term as an example. That's all. You could have even chosen t square or t power 4. I just wanted to have something that is t to the power anything other than 1. Okay. Now, suppose I want to predict temperature distribution on a cooking pan. What will be the source term? Well, the source term might include a radiation. Okay, so it may look something like s equals maybe some a times some t naught to the power minus t to the power 4, right? Where t is the temperature of the pan. Okay, then how do you linearize this thing? You linearize s as a linearize as you say s star plus partial s by partial t star times t minus t star, right? So you basically write this as evaluate this term at star values, current rated values, take a derivative and evaluate at star values, and then multiply that t by t star, and then you gather the terms and write it as sc plus sptp. Okay, so then these are your sc and sp terms coming from your basically linearized source. Okay, all right. So let me go and see if I can answer the questions in the chat box. All right. Okay, so we have one question here from Mohan. Is there any further live session? If there is any, it would be helpful. Well, I can do maybe one more live session or something. I'm not sure. We'll see if it is required. We can have one more live session. Will you conduct any SQL course subsequent to this course with advanced concepts? Not sure yet. We will see. If I mean, I have not thought of anything. Maybe in the next 1 year or something, we can have a SQL course for this if it is required. I would suggest if you can, kind of give me feedback in terms of what course would be useful to you, then I can do that. Let me kind of stop sharing this thing so that it doesn't go. Okay. All right. So let me go back. Stop share. Okay. All right. Excuse me. So when we solve compressible turbulent flows, how many unknowns we will have and how many equations we would solve? Well, essentially, if you have compressible flows, you have the number of unknowns is your density, 3 components of velocity, and pressure and temperature, right? So these are the unknowns, and then equations are your conjugate equation, same number of equations. It's only that you will have another equation for your density, right? The conjugate equation for incompressible flows, it would be just a compatibility check, right? You have del dot u bar equal to 0, whereas for compressible flows, you have dou rho by dou t plus del dot rho u equal to 0. So the conjugate equation or the conservation of mass will be an equation for density. That is the only difference. Of course, the methodology of how you solve will also be different, okay? Whether any areas are there, I can do independent research in CFT without any partial validations, only pure theoretical research. I don't know. I don't understand the question. Practical validations. Well, only theoretical research. I don't understand. Maybe, I mean, you can always do independent research, but I would suggest you kind of look up some literature. So, or you can look at, some good research articles that usually come up in maybe Popular Science, or you can look at Annual Review of Fluid Mechanics. These papers are written by experts. For example, if you look at Annual Review of Fluid Mechanics, there will be several review papers, and these papers will review whatever is there in that particular area. For example, some droplets, sprays, or some methods, all these things. So you can read them, understand what are the, what is that you interest you, and then you can start maybe pursuing research in that direction, for your higher studies maybe. What are typical schemes used for solving CFT for compressible Navier-Stokes equations? Again, that kind of depends. You have schemes like ENO schemes, essentially non-oscillatory schemes. You can also use compact schemes and so on. It depends on whether your compressible flow that you're solving has shocks or not, and so on. Okay, so it kind of depends on all those things. Then in the assignment 11, question involving flow through porous medium, the continuity is UA equals constant, but the pressure gradient causes the flow. If there is any pressure gradient, then velocity should increase. Yeah, velocity might increase, but the area is also given to decrease, isn't it? As a result, U times A, the continuity equation has come out to be. It's not. Is it the continuity equation? I have to look it up. But I think if the area is increasing, the velocity would also change, isn't it? Well, the continuity equation is not just. Is it just UA equals constant? If it is 1D, the thing is, this problem is set up as a 1D problem, but the area is changing. As a result, U will change, right? I think that is the question. You can write to me, not clear. How do CFD application engineer conclude what is happening by seeing the contours obtained from post-processing in terms of product design and development? Well, okay, so if you want to, there are several things. One is if you look at, let's say, post-processing, you can look at maybe the contours of velocity and see where the velocities are smaller, and similarly the pressure. But you don't usually just look at the post-processing values. Okay, you also look at the integrated quantities, such as what is the total drag acting on a particular object, or what is the total stress, and things like that. Total drag acting on it, or total coefficient of pressure, and things like that, or where is the heat transfer larger by looking at the Nusselt number and so on. Okay, so if you want to look at purely from the contours, then I think you have to look at the contours will kind of help you where is there is a region of, let's say, a high values or low values, okay, or how is the different terms distributed within the domain, okay, and so on. So it's kind of, I don't know if I kind of answer your question or not. So when it comes to product design, for example, let's say you want to design, let's say, the washing machine or something, right? Inside you want to kind of increase the mixing. So you will come up with one way of quantifying how you define a good mixing rate, right? And then you look at different designs of this washing machine, let's say vessel, such that if you place, let's say, some restrictions, let's say some bumps here and there, then is it kind of causing an increase in mixing or not? Okay, so that's how you kind of quickly can look at it, either from streamlines or contours and so on. Or maybe there is a recirculation zone you want to avoid. Let's say there's a big recirculation zone coming behind the car, and you don't want the recirculation, because if there is a recirculation, then that's going to cause a low pressure, and then the drag on the car will increase. So these things you can look at qualitatively from these post-processing. Okay. Is there any research being done for combustion in CFT, preferably in compressible flows in IITM? I don't work in combustion, but there are other faculty in the thermodynamics and combustion lab in IIT Madras in mechanical. You can look up who work in combustion in CFT. Okay, or you can also look up people in aerospace department who also work on combustion. Okay. What are the major research areas in CFT being done at IITs or other universities abroad? Well, major research areas are nowadays, we are kind of shifting towards eddy resolving methods such as LES or DES and so on, such that you can have a hybrid method, in terms of turbulence modeling. The areas are kind of vast, so I cannot give one or two areas. As I said, there are several areas. So what I would suggest is to Abhijit is basically you can look up maybe some of these annual review of fluid mechanics and see what are the major research areas, and then you can kind of will be able to connect them to the what is being done in the Indian institutes here. Okay. Now coming back to the essentially, if if the area is there are several challenges in any of these areas. So even if you pick up a small area such as, let's say, pure fluid flow without even involving any heat transfer or multi-phase, there are several challenges in terms of numerical methods, getting the speed, how do we solve it quickly. So all these things are there where research is kind of being pursued in all these institutes. During the iterations, are the corrected velocities and corrected pressures without interrelaxation satisfy Bernoulli's equation for every iteration? No, I don't think so. So Bernoulli's equation. So the thing is, Bernoulli's equation is only valid for if you have a steady flow, incompressible flow along a streamline, and if you have an irrotational flow, right, or inviscid flow. So unless you satisfy all these things, you won't get to Bernoulli's equation. But what we're trying to solve is we're solving Navier-Stokes which has friction, so which has mu, the viscosity terms, so it will not satisfy Bernoulli's equation. But some of the 1D problems that we are doing, you might be able to get something from Bernoulli's equation, but I'm not sure. I haven't tested it, but I don't think that is the correct way to do it, because all the questions in the assignment are set up such that you will use the simple algorithm or such, or something like that, so that you can solve and get the answer. So if you use Bernoulli's, you may get something else, but that you may not find the answer in the options that is given. Okay. Next question from Mohan is that where can I see the recent research and their publication in CFT? Well, I think if you look up, if you're talking about a particular faculty, you can look up their web pages, or you can use any of the ISI Web of Knowledge or Google Scholar and look up all the, and kind of check box 2018-19 onwards, and then you'll see what are the research that is being done, right? You can kind of put in a keyword CFD or CFD of combustion or something like that, and then that will kind of give you. What do you look for one who is applying for any such masters? Okay, so if somebody is applying for, we basically look for some basic understanding of, let's say, fluid mechanics, heat transfer, or thermodynamics in the interviews. So if you have some basic knowledge of at least 1 or 2 subjects, you'll be able to answer, kind of think and answer some of the questions rather than, throwing them back from memory. Okay, so that's what I think people look for in interviews. Any CFD journals or magazines are available for specific for CFD. So you have CFD online that has several forums in terms of for each of the software such as Upwind or Star CACM and things like that. CFD journals, there are many journals, several journals. You can kind of look it up. Magazines, I don't think there are any magazines. I'm not aware of them, but you can look up Annual Review of Fluid Mechanics or Physics of Fluids or any other popular science or current science and journals like this, which will also have a part of CFD in there. Okay. Oh, can you suggest any book which explains collocated mesh approach? You can look up this book by the finite volume method by Mokald, okay, and Mangani and Darvish that I have written, but that's little more involved. I don't know whether you'll be able to completely understand. Not sure. I think the book by Westing and Malalasekara has some strict treatment of the collocated mesh. So if you pick up the latest version, 2018 version or something, it has collocated mesh. Only thing is that it is somewhere in the later chapters. Chemical engineers are being taken in to your CFD group at IIT Madras. I don't work in chemical reactions and stuff like that, so I don't recruit. But I am sure there are several other chemical engineering faculty who would be happy to recruit chemical engineering students. Okay. Is it wise to develop one's own codes for use than open source CFD codes and incorporate editions or what? Well, I think it depends on what exactly you're looking for. For example, let's say depending on the time frame when you want to get the results and depending on the problem you want to solve. So if there are already open source CFD codes available, such as OpenFOAM or other things, then it is certainly wise to kind of use those codes and do it. But at some times, at some point, you might feel that the changes you want to make in these codes might not be straightforward because they are written in a particular way, and then if you want to change it, you have to kind of come from top to bottom, all the way you have to change at the bottom, which is probably not easy. So in that context, then you end up with writing your own code. So it all depends on the problem you're trying to solve. But it is certainly a good idea to start off with open source CFD codes and then move from there, rather than trying to write something from scratch, which might be a very big goal. Okay. And we have another question here from Jayant. Can you share your experience of working in ANSYS? Okay, I think it's not relevant. It's exciting. I enjoyed the work very much. Okay, so it's very enjoyable work while I was at ANSYS. Okay, what does the Lattice-Boltzmann method entail about? So Lattice-Boltzmann method is a kind of an alternative method, okay, which is also used in CFD, which is being popular for the past 3-4 decades. In which a discrete lattice is used, in a discrete Boltzmann equation is used and solved, and in a particular limit of the Knudsen number, we can recover the Navier-Stokes equations. Okay, so Lattice-Boltzmann method is basically a kind of a weakly compressible solver that can be used for performing incompressible flow simulations. Okay, one big advantage of Lattice-Boltzmann is that it is kind of easily parallelizable, and that is the reason why it is kind of gaining popularity over Navier-Stokes equations. But Navier-Stokes equations has its own classical nature in solving the problems. Okay. Okay, I'm kind of waiting here for more questions from the students. How we will do simulation of rarefied gases? That's anyway, that's a kind of a completely different topic. You have to look at the, basically in rarefied gases, you have particle-particle collision. So you have to kind of start modeling, the collision of the particles. So we will not be using a continuum-based approach. So we will be using something else, basically a particle-based approach that doesn't fit into this particular course as such. Okay. Meshless methods, I haven't worked with them, but I think meshless methods have, they don't have a mesh as we define, but then you have a cloud of points, right? You basically have a cloud of points using which you have to kind of interpolate. So meshless methods also has some kind of a, they don't have a mesh, you don't connect and have edges and faces and lines and so on, but then you have certain nodes which are all like a cloud, right? So they are there. So I haven't worked with them, but then you end up writing two-dimensional or three-dimensional interpolation functions to get value at one particular point coming from all other points. Okay. Okay, then we have another question from Ujjwal. Although PISO method was developed for unsteady compressible flows, do they work in incompressible flows? What computational time and accuracy? What about computational time? So PISO methods were developed for, yes, I mean, they are developed for, they do work for incompressible flows as well, right? And then, well, the computational time and accuracy requirements depend on the methods that you use, okay, and also the problem. So I cannot really comment on that part. Then the question from Bharat is: are there any books which talk only about fluids physics, which describes their behavior without talking about mathematical treatment? Fluid physics. So basically, you're talking about a fluid mechanics book without equations. I don't know. I have to look it up. Maybe can you post this question in the forum? We will see if we can find some books. Maybe some of the popular science books will have no equations rather than just explaining how things work. Okay, maybe that is something you can kind of look up maybe. Because every fluid physics book you take will have some equations so that you can explain what you are observing. So okay, if you want to just look at the pictures, then you have this Van Dyke's book on flow visualization, which will kind of show you how a flow looks using some visualization method for, let's say, flow past a cylinder, or some of this flow or an aerofoil. They will just show you streamlines and all. So you can look up this book by Van Dyke, a fluid mechanics album, a fluid motion album or something like that. It's a very classic book, probably very old. It's also very expensive. Okay. Okay. In assignment 11, pressure gradient comes to be 2.625 as against 3.75 given the options. Okay, I have to look it up. I haven't calculated it. Maybe I'll calculate and then. Can you post Dr. Anthony in the question forum so that TAs and I will take a look at it? Okay. All right. Then what question from Somasani Mahesh is what skills are required to become a CFD developer and what is the scope in India? Well, I think if you have good programming background in terms of, let's say, C, C++ or Fortran and things like that, I think that is sufficient to have a good developer in CFD. Other things you can probably learn on the job. Okay. You can also look up how OpenFOAM is basically maybe written. Okay, you can look up how the code is written and how it is managed and things like that. That might also help you. Then another question from Dr. Anthony is pressure correction algebraic matrix is singular. I don't know. Okay, which one? It should not be. So okay, if the matrix becomes singular, then you can fix one of the pressures, right? You can fix one of the pressures and then calculate everything with respect to that. Okay, that's how you would do it, right? Essentially, you have both conditions are given for maybe for there is no pressure boundary condition given, both are velocity boundary conditions given, then it will become singular, right? Okay. Then the next question is that is what I was looking for exactly. Okay, I'm not sure. Okay. Okay, the book. Okay, so you can look up the book. That is the Van Dyke's book. Kindly mention about turbulence modeling reference books. Well, there are several reference books on turbulence modeling. I think if you just Google, you'll get like tons of books. You can pick up the book by turbulence modeling by Wilcox, Wilcox. It's a very famous book. It's a very nice book to read as well. So you can pick up the book by Wilcox, or if you want, you can pick up the book by Turbulence by Stephen B. Pope. Okay, S.B. Pope, P-O-P-E. That is also a good book. Then the next question from Pramod is in incompressible flows, the pressure difference only matters. Yes, that's correct. Only the pressure difference and the length. So the pressure difference or the pressure gradient only matters. How does a fluid particle know what pressure in downstream before even traveling to that point? it may not know what is the pressure downstream, right? It will only know. So the information propagation is happening because of the speed of sound, right? So the minute pressure fluctuations are the speed of sound, right? And that is how it kind of senses, right? That's what kind of changes the equations when you go for compressible flows, right? Because the flow is happening much faster than the speed at which speed of sound travels, and that's where it kind of differs. Okay, very good. I hope I'm kind of answering your questions correctly or accurately. I'm waiting here for more questions. Can we contact you in future for some help? Yeah, sure. I mean, if you want, you can write to me. I don't know if I can help immediately or something. I may not be able to look into your codes or something like that, but if I know something, I can certainly refer you to a particular paper or something like that, or a particular direction. Certainly, you're welcome to write to me. Please write to my email address. I will reply as soon as possible. Okay. Then another question from Jayant is, will we have continuation of CFD course by you? Thanks a lot. I got to learn a lot from your lectures. Thank you so much. Yeah, thank you for your compliments. I don't know if we have a next course on CFD as such immediately, but I will try to offer this course again so that more people will be useful to more people, maybe in the next year or something like that. I think many students could not register to this course because of the lockdown and they are not in their college and things like that. So I hope next time when it is offered, probably there will be a larger turnout. Yeah, but if required, I would offer another course on as a sequel to CFD, as somebody asked, or as a precursor to CFD, such as numerical methods, something which will basically help you, with the programming part of numerical methods. Then next question from Ujjwal is, hi sir, what are your current research areas in your group? Okay, so we are working on turbulence modeling using larger simulations, also on the lattice Boltzmann methods for fluid flow and heat transfer, and some of my other students are working on biofluid dynamics, such as blood flow in the human arteries and so on. So these are our areas. Next question from Pramod is, how does the fluid particle know it should start at a higher velocity without sensing there is much lower pressure in the downstream? Well, okay, so the thing is, it doesn't start at a higher velocity. So basically you have a high pressure, right, for a fluid particle, and it is traveling at certain velocity. So the forces acting on the fluid particle would be there is a differential pressure acting on the fluid particle, right? That is what will drive the, together with the velocity, that is also helps in driving the flow downstream, right? And what is acting against the fluid particle is the fluid friction. So you have a velocity which will give you the inertia, and then you have the pressure difference which will also push the particle, whereas it is kind of facing the friction. So as a result, balance of these things, which is nothing but given by your momentum equations, will help, in making the fluid particle move in the forward direction or in some direction. Next question from Omkar is, does strain rate depends on the fluid rotation in a domain? Well, fluid rotation is different, strain rate is different, right? So strain rate has a plus in the equation, right? You have dou v dou x plus dou u dou y, whereas the fluid rotation or the angular velocity has a minus, right? If you look at omega. But I think Omkar's question is related to if you have a rotating fluid, then will the strain rate change? Yeah, I mean, of course, it might change depending on what kind of rotation you have, whether any rotational fluid movement or it is a rotational one, depending on whether it is a solid body rotation or not. Next question is, although we treat finite difference is treated as historical method and more accuracy, why are we not using them in place of finite volume? Well, finite difference methods are also used. It is not in place. Finite difference methods are very easy to learn, easy to code, and more suitable for teaching purposes, such as pedagogical purposes. Only thing is that applying the finite difference methods to complex geometry is not straightforward, right? Because you don't have a particular direction for a complex geometry. So that's why commercially or on a large scale, finite volume methods are more successful, although they are not although they cannot be made as accurate as finite difference methods because of the complexity with which meshes can be generated for complex geometry. Okay. Next question from Abhijit is, it was one of the finest theory class ever. I attended. Thanks a lot. Expecting your sequel online for sure. Thank you so much, Abhijit, for your kind compliments. So if something is required, I will certainly make another course on CFT. Otherwise, as I said, I will go back and make a course on numerical methods, which will also involve maybe some programming, and you can learn something there. Okay. All right. Next question from Bharat. Okay. I'm not sure if if there are books which will contain these concepts. See, for example, instabilities is a very mathematical, or it kind of borders on applied mathematics and mechanics. So, and wave propagation is also a very mathematically oriented book. So, I don't think there are any books. You might find some physics without a lot of mathematical treatment, but then there will be some equations. Okay, you can pick up books by for instabilities. You can pick up maybe books by I'm unable to recollect at the moment. Yeah, I think wave propagation. You have a lot of books. I think you just have to kind of search for them. Okay. Next question from Dr. Anthony is how to validate DNS. Well, I mean, you can use experiments to validate DNS. Okay. Experimental data. Another question from Omkar is, in conjunction with the above equations, does solid body rotation will contribute to shear stress in the field? So essentially, if you have, okay, so shear stress, basically if you have, let's say, strain rate, then you have shear stresses coming, right? If you have strain rate, that means if you have deformation. So if you have, let's say, a free vortex, right? And a force vortex. I think you know the difference, right? If you have a free vortex, so or a solid body rotation, right? Then you don't have any strain rates, right? Basically, the fluid particles are not rotating about their center, right? They're only going around the circle, right? Otherwise, if you have a force vortex, then you have some shear stresses, right? I think you can pick up a book by Hawk and McDonald or Anton, and then you'll be able to figure out the difference between free vortex and a force vortex. Next question from Mahesh is, what is the difference between pressure-based and density-based solver? So essentially, everything is driven by, or everything is based on the pressure. In the pressure-based solver, for example, you don't have a pressure. You have a pressure Poisson equation, and these are basically the terms used by fluent assets. Okay, so in the density-based solver, all these equations are normalized with rho, right? And you have changes in density. So density is the one which will kind of come from the continuity equation, mass conservation equation, and it will kind of flow down. In the pressure-based equations, you will still write a pressure Poisson equation like we do in the incompressible flows. Although some changes in density are allowed, you will still solve for the pressure Poisson equation. Okay. Yeah, Physical Fluid Dynamics by Tritton, maybe the book, possible. Maybe you can pick up this book that that Bharat Prem is looking for. Maybe you can pick up the book by Tritton, titled Physical Fluid Dynamics. Okay. Next question from Mohan is, can you tell me to visualize vector field for a given velocity field in a rectangular domain? Is there any simple tool to view velocity field? It's like plotting velocity field alone. You can plot velocity vectors if it is possible, maybe using, let's say, ParaView, or maybe using TechPlot or something like that, right? You can plot the velocity field, or if you want, you can also plot the streamlines that accurately describe the velocity vectors, right? So you can also do that. Okay, thank you, Ujjwal. Thank you for your comments. Okay, I think we have it's 7 o'clock. Maybe if you don't have any more questions, shall we call it a day? If required, we can have another session so that we can interact again, or we can also interact through the questions, the question in the forum as well. Please write the name of the author that you recommended, Bharat. It is Tritton. Okay, so I'll just share it again. It's the uh, physical fluid dynamics by TRITT1 written. Okay. Uh, experience in Purdue. Well, it's a great experience. I learned a lot of things there. Uh, I don't know if I can say a lot of things here as such because this is probably not the right forum. But yeah, I mean it's a great experience in terms of doing a lot of courses and research and things like that. Okay. Any more questions? Anybody? That's all. Okay. Thank you. Thank you so much. Thank you, Pramod. I'm happy that all of you found the course useful and valuable. I hope no problem. You're welcome. If you guys have more questions, please write on the NPTEL forum. The teaching assistants will tell me, and I can answer you as well. Okay. Thank you, Bharat. I'm glad that you enjoyed the course. Oh, Van Dyke. Yeah. Okay. So Van Dyke is I think it's called an album of fluid motion by Van Dyke. Okay, that's a nice book. You know, if you want to just look at the beautiful pictures of fluid mechanics, you can pick up this book. Yeah, an album of fluid motion. Yes, I think Ujjwal has written it here. Thank you, Ashok. Okay, sure. I'll ask the NPTEL team to put up another session. Yeah, but I would suggest all of you to kind of practice the assignments. I told the TAs to post all the solutions, so please go through them and for your exam. And also because on the live session I can answer some questions, but not all of them because I can't start deriving a lot of things. So most of your questions will be answered through the forum, through TAs and me. But if you have some general questions, we can discuss through this live session. Okay. But please practice all the questions, and I will ask TAs to post all the solutions for the assignments, and you should go through the solution step by step so that you can answer in the exam as well. Okay. Apart from the course, I have also learned more about the art of teaching. Okay. Thank you very much. Thank you, NI3K. Okay. And thank you, Prashanta. And okay, I'll conduct another live session. Exam is on 20th December. Yes, it's on 20th December. It will have all multiple choice questions similar to your assignments, and it will have certain weightage from your, what you have done from the assignment, what you have learned while watching the lectures, and some will be something new. But they will be all on the similar lines to similar to what you have done in the assignment. So please practice all of them and go for the exam and see as much as you can. Okay, what you can do in the exam. Thank you, Abhijit. Okay, there will be choices. There will be 4 or 5 multiple choice. It's a multiple choice exam, so all the questions will have multiple choice. Yeah. Yes, you have to answer all the questions. Yes. So all the questions are of MCQ, multiple choice questions, and I think it will be 50 questions, maybe 50 questions if I'm not wrong. Yeah, 50 questions for maybe 100 marks or something. No extra questions. You'll have only, you'll just have some 50 multiple choice questions and you would answer them. But then you will go in a particular, just like your assignment, you will go in a step by step. Like, first question you write the equation, second question you substitute for the numbers, and then, write the, calculate the values and things like that. So it is important that you look at the assignments carefully before you go for the exam. And the solution, whatever is provided. Okay. Okay, thank you, Bharat. Okay, any other questions, anybody? If not, we will call it a day. Any books you suggest for fluid mechanics, brushing up for fluid mechanics? You can pick up maybe Fox and McDonald's. That's a very good book. Okay, Fox and McDonald, fluid mechanics, or maybe Kundu and Cohen, but that might be little on a higher level. So Fox and McDonald might be good. Thank you. Nice talking. Nice kind of interacting with you as well, Bharat. Okay. If there are no more questions, we will call it a day. Okay. Thank you everyone for joining for today's live session, and I will see if we can have another session before the exam. Okay, so that we can discuss a few more things. All right. Thank you. Talk to you soon, and thanks for all your comments. Okay.